Hello everyone, welcome back to another lecture of Chemical Process Design and Simulation course code CHE446. And as you know, there are 4 CLOs of this course, and our today's activity is related to the simulation of plug flow reactor in Aspen HYSYS. And the CLOs we will cover are related to CLO 1, which is fundamental, and CLO number 2, simulation. So I had told you in the previous video that lecture number 16 to 18 are focused on these two reactors. In the previous video, we have simulated CSTR. In this video, we will simulate PFR, and in the next video, we will be using CSTR in series, PFR in series, and then simulating both. So just like the CSTR, there is a PFR, and we know the difference. We have rigorously studied these two in CRE subject. So this is the equation dFA over dV is equal to RA when this is a tubular reactor, when there are no catalyst involved, and when there is a catalyst involved, this V replaces with W. So the problem statement is same. The procedure for adding the reaction set will be the same. The conditions are same, but in this case, there is a difference. We do not have to specify the reactor volume. In this case, we will specify length and diameter. That we have been given that calculate the reactor length which is required to achieve 90% reactor conversion. In that case, it was the reactor volume. Here, we will be calculating the reactor length. Assume steady state a single tube reactor with a diameter of 2 inches and feed stream 100% cis to butane with a flow rate of 1 kg mole per hour, 10 bar and 25 degrees centigrade. So previous procedure will remain the same. Feed is added, only one outlet which is product, reaction set is added, and this void fraction is 1, which means that no catalyst information is needed, and obviously no catalyst is involved, because if there is any catalyst involved, we will be specifying heterogeneous catalytic, but we are not specifying it. This is the 2 inches diameter reactor length, initially 1 meter, no pressure drop. Then obviously the adjusted variable will be the tube length. Target variable, as we have seen in case of CSTR, is actual conversion, and then we get this length of 8.348 meter. So let's quickly go back to Aspen HYSYS, and I will start from the file where we ended previously. So reaction set is specified, everything is specified over here. We are not going to start from the scratch of adding the component, fluid package, reaction, but we will go to the reactor and we will select this plug flow reactor, we will add it, and we will do the connections of it. That feed is added over here. This is the outlet. We can specify it as outlet or product. Then it requires a reaction set. We have specified the reaction set. Unknown dimensions. In CSTR, it required volume, but there are unknown dimensions. But we will first specify the feed, 25 degrees centigrade, 10 bar, 1 kg mole per hour, and cis to butane and trans to butane. 1 for cis and 0 for trans. And feed is completely specified. Then the diameter is 2 inches, 2 space, this one is inches, and 1 meter length. And unknown delta P, either you can specify delta P here as 0, or you can simply say it as 10 bar over here, it's up to you. So go to this reactions, check the conversion, it is 26.12% with the conditions given. So what you need to do, select the adjust tool, I've already told you. So what you need to do, go to this all, this adjust, click it over here, and adjusted variable. Which one is the adjusted variable? Select variable. Now let me tell you that the previous problem is already in this simulation file. That's why it is giving you multiple options. The CSTR is already above here, but we are not concerned with this in this video. Or we can check it as well. It's not a big issue. Select variable. PFR 100, you need to appropriately select it. If you click on the CSTR, there could be the issue. So PFR 100, what do you need to vary? Tube length. Do not need to vary tube diameter, because in the problem statement, you have been asked to calculate the tube length for which you achieve the 90% conversion. Select it and then select variable, which is the target variable, PFR 100, and the actual conversion. Select it, target value is 90. Again, unknown maximum minimum, optional, you just start it and you see it is not solved in 10 iterations. That's why I had told you that even you can proceed with it. So now what to do? Yes, definitely go for more 10 iterations. not solved. Again 10 iterations and it has been solved. So it's better if you give the initial iterations a big number like 50, 20 or some 100 to avoid this, or you can continue with this. But obviously in a bigger problems, you need to give the iterations a higher value. So if you go to this PFR and you see in results 90% conversion has been achieved. Now, just like the CSTR example, we will see what is the residence time over here. So click on the spreadsheet, place it over here, double click on it and go to the spreadsheet, and I have already told you how to add it. First we will specify reactor volume. Obviously it is volume. Here it is not tube length, otherwise the unit will be differentiated. Flow rate and residence time. So reactor volume, right click on it, add import variable, PFR 100, and here it is reactor volume. In case of CSTR, it was the tank volume. Place it over here, click done. 1.692 multiplied by 10 raised to power minus 2. Then add import flow rate. Which one is the outlet stream? This outlet. Okay. If I take you back and show you over here that the outlet from this reactor is named as outlet. So we will click on this outlet, add import, go to this outlet, and in outlet, this is the actual volume flow. So click on it and done it. And then you simply need to write the formula, which is B1 over B2 multiplied by 62 to convert it to the minutes. Now it is 10.37 minutes. And what was your answer in the CSTR? Let me take you back to it. In case of CSTR, the residence time was 39.13 minutes. And in case of PFR, the residence time is 10.37 minutes. So if you recall your CRE concepts, you can see the clear difference between PFR and CSTR for a same conversion. So this activity can also be said as that we have compared the CSTR and PFR as well. So that's it from this lecture. We have simulated PFR successfully. In the next video, we will be continuing with this activity, that we will be doing CSTR in series and PFR in series, and then we will be comparing both two. And obviously, the result will remain the same, that for PFR, the residence time obviously will be less, and for CSTR, definitely the residence time will be high for the same conversion. That's it from this video. Thank you so much.